First of all, thank you very much for giving me the opportunity to present my work. My name is Jaswant Singh, and I will be talking about the utilization of machine learning in Sartre, how we predict the cross-section, basically at low Eck. I will be talking about the diffractive vector meson production. That is, this process is measured in HERA, ALICE, and LHC also. And basically, this is the signature of this process. In inclusive case, what we will do, we will measure the precisely electron, we may measure the kinematics fully of the electron. But in exclusive vector meson production, we will take care of all the final states, like we collide the electron and proton. What we will do in the final state, we will get the electron, proton, and the vector meson. Vector meson could be Zep, psi, rho, and phi, or it could be DVS, basically the real photon. We will measure all the final state in the diffractive vector meson production, and the signature of it, basically after the production in the detector, what we will get, there is a rapidity gap between the final state of the proton and the vector meson. And this basically, this process, when we take the t distribution of it, is basically exactly it's like the diffraction of the light from a opaque object, and we will get the diffraction pattern. In a similar case, in the DVSS, we will get in the similar case, we will get this like pattern of its like t distribution. You will get in the next slides very soon. And this is basically at HERA. This is 15% of the total DVS is for the diffractive. As this is basically do directly the EIC. In EIC have a large luminosity as compared to HERA. We can expect that there will be this factor, basically 15% will be the more, is around 30 or maybe 35. And if we have this large statistics, we can like understand very well that process. And this process is basically when we see the cross section of it, is perturbatively is basically the square of the gluon density. That basically is we expect that from this channel, what we can understand the gluon dense material inside the target very well. This is experimental point of view. Let's try to understand it from the theoretical background, that's using the dipole framework. In this case, this photon that is coming from the electron side is fluctuate into a quark-anti-quark pair. That then this quark-anti-quark pair will interact with the target, and after this interaction, it will like recombine, and the quark-anti-quark pair is make the vector meson. And this is basically, this process is timely ordered. Like first the photon emit fluctuate into the quark-anti-quark pair, then is basically interact with the target and recombine in the vector meson. During this is basically these three sub process, this convolute in this way, we get the amplitude of it, and this is the kinematics of this X is basically you can see there is a gluon exchange between like quark anti-quark and the target. Is the XP is the momentum fraction of that, and W square is the center of mass and the square of the photon and the proton. And Q square is the virtuality of the photon, and the T is basically should be the minus sign here. T is basically the transfers, 4 vector momentum transfers through the gluons to the dipole by the proton. And Z is basically the momentum fraction of the quark that is taken from the gluon in the light cone theory, light cone frame. Sorry. Now the variables is like R is the dipole size, B is the impact parameter, and this is basically our lap of the vector meson wave function to the photon of the wave function. And this the red one is the dipole cross section that we will like. You can see how these like all these things look like in a graphical way. In plots, you can very well study in the KMW paper. There you can see this, and you can understand very well about this. And the dipole cross section is looks like this. From here, from this basically this wave function of the photon that's split it into a quark anti-quark pair. That is we know from the QED, and the vector wave function of the vector meson we has a boosted Gaussian, and this is basically we will get about this. When the dipole is scattered from the electron, so dipole is scattered from the target, which is proton. When the simplest model is basically when a two gluon exchange is there. In that case, dipole, the cross section of the dipole is the area of the dipole is proportional to the area of dipole and how many number of gluon in the when the traveling to the proton, and what is the at what impact parameter that interaction happen, and we include this profile of the target. This is basically the for simplest is two gluon exchange. When dipole interact to a target is happen basically is a multiple gluon exchange there, and that is basically after this multiple gluon exchange that we will get this expression, and all this is R is basically dipole size alpha is a strong coupling constant at the scale mu square, and with how the scale is evolved at this, and TB is the target of the profile. And after we get all these things, when we put it into expression, that we will get this the cross section of this for this process. Now I'm from going to EP to EA. Basically, to understand the dense medium in the target, the EIC one of the goal is basically to understand the saturation. As we know, we don't have any signature. We are not able to get this signature of the saturation in the proton. Like you can see the Hera data. And the Alice or LSC it had so much higher energy. What we can do, we can we thinking something different one. Like in EIC, they replace the proton to a bigger target, which is nucleus. You know that the saturation scale of the nucleus is basically as compared to Hera, there is a Ohm factor a to the power of 1/3 that is have seen many times in the previous slides that other people shown you. You can see basically there is an enhancement of the saturation in case of the nucleus. So if we have a nucleus, how to understand is this process in the when we do the collision of electron and the nucleus, so that we already this basically this formalism, the dipole framework, we can extend from EP to EA. That is very well motivated from the impact parameter dependency. And this is basically the dipole that is not inelastically interact with the target, and this is, and when we go to the using the independent scattering approximation, that basically, and we model the nucleus like there is inside the nucleus, the nucleons are distributed using the wood section distribution, and when after using this, when the dipole is scattering with each nuclei independently, that we'll get this dipole cross section as this. You can see this, and this now is target is basically the nucleus, and each the dipole is interact with the each nucleons at the impact parameter B. When in the EA collision, this like in EP scattering, there is P is intact. In the same situation, when nucleus is intact as it is, we get we call it a coherent one. And when the nucleus is break up into a color neutral fragments, we call it basically the incoherent cross section. A total cross section is the sum of that. Now from the Goodwalker picture, the incoherent cross section is basically the variance of the amplitude over the average or initial configuration. Now to calculate the incoherent cross section, that we need basically the total one and the coherent one. You see, to calculate a total one, basically we are using a different numerical method analysis where we calculate the average, or we do the average or average over the nucleon configuration. Why do we do this? Basically, when the dipole interact with the nucleus, we don't know which gluons coming from the which nuclei, and we don't know the position of the nucleons that gluons emitted to interact with the dipole. That's what we do. We do this average over the nucleon configuration because of this. And one thing is that how many number of configuration do we need for the convergence? This will come in the next slides. Basically here, we can say we have basically analytical expression for the coherent one, like for this one, we have analytical expression, but we don't have for the total one. We do the numerical averaging for this, and this is like you can see the how looks like all this like total cross section, coherent and incoherent. As I mentioned in the first, like the diffraction pattern is look like this. This T distribution is basically the Fourier conjugate to the B, basically the impact parameters where the interaction will happen. As we can say, we can access the spatial structure of the target because of this T. Now, up to now, whatever I explained, that is basically the physics of the Sartre that is implemented. Here, basically the Sartre now is currently only exclusive vector meson production for EP, E and UPC also I didn't mention, but there is UPC collision also. And the physics I already explained you that there is a technical detail for it. I will come to later about this point, that 3D lookup tables that is used by the Sartre to generate the events. And this is open source software, you can get easily, and you can do also simulation for this process. And the developer is my guide, supervisor, Thomas Ulich. And the detail of this software you can get basically from this. Now the thing is that the Sartre have the basically the two things, the table generator part and the event generator part. Now what we do, if you want to generate the events using only event generator without table, you will, like if you run today, you will get the result of like in a month, or like it will take lots of time. That time, because you see there is a 4D dimension integration for each point, and there is a 500 configuration for each. You can see from here, for the convergence we need a 500 configuration. And when we do this for a simulation, it will take a lot of times. To save that time, what we do, basically I already done it. First we create the tables where we store the amplitude with each kinematics point like Q square, W square and T. With respect to this is store the amplitude for it, like for transverse and longitudinal, and first moment and the second moment also. First we create the tables, and then these already produced table we use as an event generator. You can see the benefit of it using these tables. We can generate the millions of events in a 10-second or a fraction of seconds if we use these tables. If without these tables, it's taking lots of time, like months and all. And this also basically the tedious work is to produce these tables. Currently, they produce like US Science Grid. They already produced for the gold and for the calcium. And this takes more than 6 months to produce these tables. So to overcome this basically a time, what we do, we will use a different techniques, and you can see how these tables look like this. This is basically kinematics, and this is 3D tables. These not tables is basically the 3D histogram that is used by the Sartre. When we generate the events, Sartre call these tables. This is one of the example that we have lots of these. Sartre use these tables and generate the events. And basically during generation of the event, what it will do, you can see there is basically kinematics already stored, but in this point there is no any kinematic amplitude stored. What it will do, there is a trilinear method that is implemented in this. Basically during that event generation, it will use that method to predict the value in between these points. And you can see there is lots of gap also, and we can it's predicting very well, but it's not like not so much well. So that's to do this we use a different technique, so that first we can generate tables quickly, and we can predict very well. We use the machine learning. That is the overview of it. It's basically, it is architecture of these are the inputs and these are the layers that I used, and 3 input layers, and this is basically the output one. This is the loss function. Loss function is basically it will compare your value like true value and the predicted value. If true value and predict value is not matched, it will train the network. That is the basically use of the loss function. And here is that to use the training loss curve. Training loss curve is very important for the machine learning. If we understand it, basically it will tell you how basically your how you will optimize your network. Whether it can, without using this, it can be like overtrain or undertrains. That this curve is basically very important for this machine learning. Because of this, you can understand where you need to stop the training. And this is basically the average relative error loss curve with respect to data. Data is means the table already produced. When we take the like 2% of the table, we get less like higher the errors. When we take the more and more data, that we will take the we will get a low and low error. Here, after this 10% of that, we are getting the same error. So we already the tables already we have. What we will do, we will use the only 10% of it. On the 10% of it, we will train our network and predict the another tables. Only use the 10% of it, and we predict a full table. Like you can understand, only using 10%, we no need to produce the whole table now. We only produce the 10% of it, like few bins, and on that few bins, we will produce the like we can now in our hand we will make the any tables with any number of bins. In the previous method, basically, with the if your number of bins is higher, that is now time will enhance. It will take lots of time. Now we don't. Now we only use the 10%, and now by using this 10%, we can produce the whole tables by using the machine learning. These are the errors basically after the prediction, and the distribution of average relative error with respect to each kinematics point using the only 10%. Where the spikes is where the basically cross section is very small. We can say that this is the inability of the network predicting very well where the cross section is very small, and then now still is basically under 4%. And these are the tables that Sartre use it for the event generation. For this, we use basically this method we use for the gold, and by using this method for a gold, we develop like for a calcium also. You can see the errors distribution of with respect to each kinematics point, and these are the tables that we have produced for the calcium, and we also produce like only the marks and bills produce the 10% of the existing they give us, and we will provide the full table for the Sartre for the event generation. Now up to now basically the Sartre can simulate the for exclusive process also, but we are adding this process inclusive diffraction also. Basically in this case, electron like EP collision goes to EP, proton remain intact, but in case of vector meson, we will have basically the fragments of the color neutral particles. We will basically, this is work in progress. We are adding this process in the Sartre. It's coming soon. This basically you will get this process also inside where you can simulate the inclusive diffraction also. And for this, basically the thing is that during this event generation of this, the one thing is that it's basically taking too much time as compared to exclusive vector meson production. Because of there is lots of integration involvement, and there is basically 4 and 5 variables also. Currently we are not including NLO because we just in last like in 30 January we get this paper. We will implement this calculation in the future in this event generator. Currently basically in for exclusive vector meson production, Sartre use the 3D tables, but we don't have 5 or 4D table because in inclusive process, we need like, you can see from here, we need x, q square, beta and t 4D. And even we are going to up to 5D like xp dependence also there. When we will do, we have a 4 and 5D, but we don't have any root histograms for 5D and 4D dimension in the root. But we will find a way, like in a MATLAB also, if you want to the higher dimension to interpolate, what we are doing is basically to make the grid of it, and using this grid we can interpolate that. Basically when you do the interpolation for a 3-dimensional, for a single point you need 8 points for that, And when you go to the four dimension, to predict the single point, you need is like 16 point, and for the 5 is 32 points. That is very challenging for us to predict it. So what we will do, first we will make the small table using interpolation. First we will make the tables using this method in the Sartre. Then we will train our neural network for that, and we will basically make the full table for the inclusive diffraction, and we will do the then Sartre will work on the completely machine learning after that for inclusive process also. And let's summarize it. Basically, by using machine learning, we save our 90% time to produce the event or the tables. And in future, basically, we currently we have only dipole model. We parameterize it, but we want that this is also a work in progress. We are working with the dipole model. We want to replace with a neural network. And for inclusive, we are working in this is also working in progress. We are implementing this machine learning for inclusive diffraction also.
Thank you very much. Questions?
Thanks for the talk. I just wanted to understand your machine learning thing. So you have this 10% data that you create, and then how do you train them, and then you are now planning to go beyond the dipole models. How do you do that actually?
Basically, we have tables, and we take the 10% of it, and we train our network on these 10%. By networks will take its example of this as example, and but then we can predict full tables for that. That's how we do.
But depends on the data that you have, the training data. How good it has to be to train for predicting new means beyond your dipole model or something.
I'm not getting actually.
The training depends on the quality of the data, right?
Yes.
Yeah,
yes, we select the data basically.
Okay.
Yes. That is one of the part of the machine learning for selection of the data. If you choose the wrong data, that your network will the wrong training will be the wrong, then it will predict the wrong answer.
So
the data selection is there.
So how do you select those data?
On the I already saw in the
I couldn't.
Kinematics and this basically is there. How we basically there should be for each data point there will be the amplitude. If there is some these tables already satisfy the basically data for the vector meson production.
And then I didn't understand the last point you made. So you wanted to go beyond the color dipole model.
Oh, okay. That's basically currently. Let me sorry. Here is basically the now we are using this parameter this. Now we are using this, but we want to replace this with the machine learning, the entire things with the network. And we take all this as a.
But that training data you generate with this kind of interactions, or how do you generate them?
We for this we don't need tables. We use as input R, mu square, and B. Okay. And we predict the cross section, the total cross section. In that case, basically, we want that's how really dipole in the mathematical form of the dipole.
More questions? You don't let me get my gymnastics here.
Okay, so these dipole cross sections, they are fitted to the inclusive DIS data. So yes, so if we have a neural network or some architecture to just see if we don't have any bias and try to see, so it will be the inclusive DIS data that we have to fit.
Somebody else? If not, I have one. If you would be so kind to go back where you show the different kind of modifications of the dipole lens and what was the original kind of diffractive pattern.
Where?
Yeah, this one, exactly. So you need with 500 you get kind of a nice,
Yes.
yeah. Now, what I'm surprised, if I look to the 500, the diffractive pattern looks very different compared to what is shown on the right side.
This is basically total one, but this is the separate one.
Say again?
This is basically only for total cross section, but this is basically for like coherent and incoherent.
Yeah, I know, but what I'm kind of aiming at, because you know we have problems to suppress the
Yes.
incoherent to get to see it.
But at higher value,
Bubbles.
higher
Exactly.
value of 2.
So now, if I look to see patterns, a diffractive or coherent pattern with your 500 kind of samples, is this the final result? How it looks at the moment for the?
Yes, for this is now this is for 500.
Wow, that will be even harder
yes,
than to
yes, you
suppress the.
Yes.
So for coherent,
This
we
is-
could do an analytic averaging. So it's just the total, the second moment of the amplitude. So that pretty much
Yeah, but-
converges in
Yeah.
500 computations.
I understand, but what I'm kind of, so you have here this kind of, and you basically don't see any bumps anymore at the high T.
Yes.
Here that was what, and in the original kind of simulations with Sartre, it was more looking like this guys here.
Yes.
And your new simulations basically show, okay, this one here, the very small, and a little bit, and then it becomes pretty flat. This is what your new simulations are looking like?
But this is total cross-section, sum of coherent plus incoherent.
Ah, it is
Yes.
a total. Oh,
Yes.
stupid, it's even written there. Then thank you very much for the nice presentation.